Well, greetings, everyone. We're just getting settled and letting folks into the webinar. If you're just joining us, just give us another minute or so to get everyone settled and we'll get started. We have an excellent webinar and information for you today. And I have to say, while we're waiting, that I'm very excited for our 75th anniversary conference that's coming up in early the first week in November down in Orlando. We had our spring meetings with the IWCS board and technical committee for IWCS, and we went through all of the abstracts. We had over 100 excellent technical abstracts, and the content for the conference is going to be very, very good this year. Plus, we're going to have a lot of fun. We're going to celebrate our 75th with a fun celebration on the Monday evening, a Cirque Royale entertainment and stuff. So we got all in the mood this past week. So more about that later, but we hope you're making plans to join us. So again, we're just waiting for a few folks to join. Let's go ahead and get started. A few welcoming remarks. Again, welcome. We have folks from all around the globe, so good morning, good afternoon, good evening, and some of you late into the evening, so hopefully you have a glass of wine or a beer or something and they'll stay awake for us. But anyway, greetings. My name is Dave Cadieux. I'm honored to be the CEO and director of IWCS, and I'll host today's webinar. A few housekeeping items. One, as an attendee, you're part of a larger audience. So during the presentation, all the participants will be in listen-only mode. And also, this event is being recorded for rebroadcast. It will be available for viewing on our YouTube channel, but also through our website. You can see this webinar as well as all of the previous webinars. So feel free to share that with your colleagues. We encourage you to submit written questions during the presentation using the chat panel. So click on the chat, and on the right of your screen, type in your questions in the space at the bottom, and be sure to hit the send button, and we'll address your questions, time permitting, at the end of the presentation. So again, our webinar series event is hosted by IWCS Cable and Connectivity Industry Forum, and we offer a series of webinars on important trends and technologies from the perspectives of our supply chain technology leaders and sponsors of IWCS. And typically we take some of the good papers that we had in our previous conference in Pittsburgh and share them with you in these webinars. So today, we're honored to have Devin Whalen, a product engineer from Proterial Cable America. He's located in New Hampshire, USA. Devin will be presenting his paper on evaluation and refinement of finite element analysis techniques for thermal cycling of fiber cables. A helpful tool that was very well received in Pittsburgh. Devin is a product engineer at Proterial. His work includes specialty cable design, developing and maintaining test automation software, and R&D projects with a focus on finite element analysis to predict cable performance. He earned a Bachelor of Science and a Master of Science in Electrical Engineering from Bucknell University. That's where I went as well, so I'm very proud to have Devin with us, and where his graduate research focused on microgrids, wireless sensors, and energy harvesting. A great set of topics that we'll be exploring at our conference again this year. So we welcome Devin to join us, and take it away.
Thanks so much for that lovely introduction, and thanks again everybody for joining me. Once again, my name is Devin Whalen, and I'm a product engineer here at Proterial Cable America. And today I'm going to be talking about the evaluation and refinement of SolidWorks finite element analysis techniques for modeling the effects of thermal cycling in optical fiber cables. I'll start by giving a little bit of background so you understand the why before going over the how and the what, as well as the problem statement. I'll go over some important key metrics, including the coefficient of linear thermal expansion, as well as excess fiber length. I'll touch briefly on some previous work that this project builds on, and then I'll explore how we improved on that previous work, improvements we made to our simulation model, and finally the results and conclusions that we came to. So before getting into the problem statement, it's important to understand a little bit of background. In optical fiber cables, it's well known that external tensile loads generate mechanical stress, which in turn leads to increased attenuation. But that mechanical stress can come from internal sources as well, such as the fibers pressing up against one another, up against the aramid yarn, or the inside of the jacket. And that internal stress is a lot harder to measure because it's, well, inside the cable, but it still leads to attenuation, so it's something we'd really like to minimize. And that's really where simulation and finite element analysis come into play. Temperature cycling provides a useful stress case for modeling this stress. Reliable fiber cables all have to undergo temperature cycling without significant signal loss, so it's also just a very relevant process for producing good cable. As the temperature drops, the jacket will contract according to its coefficient of linear thermal expansion, or CLTE. Meanwhile, though, the silica fibers remain stiff, and as that jacket contracts, they get forced into contact with one another, as well as the aramid and the jacket wall. And as Ashfaq iterates here, those differences in CLTE between fibers and insulation create stress in the cable, which in turn leads to attenuation. This then leads into the next big factor, which is EFL, or excess fiber length. So in loose tube fiber constructions, the fibers are pulled in alongside aramid yarn, and the tension that we put them under during this process influences how much slack they have. And EFL is actually created then when the jacket shrinks during cooling. At Material, we measure EFL by bunching and clamping the ends of a longer 6-meter section of cable to keep the fibers locked in place. We then cut a shorter 3-meter section from the middle of this, ensuring to cut both ends at the same time, and that just keeps the fibers from biasing or contracting in one side versus the other. Once we've cut this smaller section, we remove the fibers from the jacket, and we measure how far past that 3-meter length those fibers extend. And however far past the length of cable that we cut that those fibers extend is our excess length. You can see that in that bottom right figure. The distance which those fibers are sticking past the tape is the excess fiber length. And in SolidWorks, we can model excess fiber length with an equation-driven line where the amplitude corresponds with the amount of excess length. You can see in that left-hand figure the straight segment approximation we're using to represent EFL. And this isn't a perfect representation. In real life, obviously, the fibers will exhibit out of plane oscillations, there'll be variation, but we did find that this is sufficient for comparing the relative impact of different EFLs. And that's important because the established theory is that a higher EFL correlates with a greater increase in attenuation during temperature cycling. And that just makes sense physically if you think about it too. A higher EFL just means there's physically more fiber that's trapped in the same amount of cable volume as it's shrinking. Some work has already actually been done towards using SolidWorks to simulate the impact of EFL on loose tube fiber constructions. This study builds off of some previous work done by Henry Rice and Jacob Savoie. In that experiment, they demonstrated measurably higher fiber strain on a simulated cable with a higher EFL versus one with a lower EFL. And they also correlated this with 2 samples that they manufactured in real life. And while this was a good starting point, we really wanted to reinforce this relationship with the larger data pool. We also wanted to take a look at contact pressure as our key metric, because in SolidWorks, contact pressure is a measurement of the stress that is produced when two surfaces press up against one another, which is exactly what we're theorizing is causing increased attenuation, that it's really those stress hotspots that's driving attenuation. So the project goals were as follows. First, to refine the existing model and evaluate its accuracy at predicting attenuation due to EFL. And second, to apply the tool and predict attenuation in a new cable design, therefore reinforcing its value proposition. Our initial approach to improving the simulation's accuracy was simply to increase its complexity. So for example, in the previous study, each fiber we represented with only a single material, but in our initial updated simulation, we represented each fiber with 3 materials: a glass core/cladding, a softer inner acrylate layer, and a harder outer acrylate shell. And that layered approach more closely resembles the actual construction of optical fibers, and at the time we believed it would result in a better representation of their mechanical response. We also added aramid yarn to the model, which you can see in the figures there, represented as an extruded curved slot. We gathered the material properties for the simulation from a variety of research studies, manufacturer data sheets, and experimental measurements. CLTE specifically, since it was so important for this study, we measured experimentally by measuring the amount of shrinkage of a small 150 millimeter sample that we put in our environmental chamber and brought down to a temperature of minus 40 degrees Celsius. One of the most significant improvements to the model was through the proper definition of contact interactions. So in SolidWorks simulations, a contact interaction is what actually allows the virtual surfaces to press up against one another. Conceptually, the simplest approach to this, you might think, would be defining a contact interaction for each fiber in the 12 fiber set, contacting every other fiber in the 12 fiber set. But that approach does fall apart for a couple of reasons. First, the number of contact interactions directly drives computational complexity. So we actually want to minimize the number of contact interactions if we want our solver to converge in any reasonable amount of time. And second, SolidWorks doesn't allow for duplicate interactions. So if I have any contact set with fiber 1 contacting fiber 2, I can't have any other contact set with fiber 2 contacting fiber 1. So it took a bit of iteration, but after some experimentation, we came up with an optimized approach to generating these interactions. And you can see the map that guides those decisions there on the right. And they're not actually shown here, but in addition to those, we defined interactions between the fibers and the aramid yarn and the fibers and the inside of the jacket. This then is what our initial results looked like. And on the surface, they're extremely promising, especially examining the stress due to contact pressure, which you can see in that bottom left figure. The solver output is clearly showing where the fibers are pressing up against one another, as well as the inside of the jacket, which you can see in those red hotspots. And examining the von Mises stress distribution as well in that top right figure, the glass core/cladding, the soft inner acrylate layer, and harder outer acrylate shell all exhibited distinct characteristic stress levels. So at this point, we thought we were moving in a good direction with the simulation. But while the simulation was significantly more complex than the original, it still presented several issues. Even after reducing the mesh resolution, a single run required approximately 13 hours to solve, which is a long time, especially if you're trying to use this tool for iterative design. But even more concerning, the simulation was providing counterintuitive results in terms of the stress versus EFL relationship that we were expecting, indicating sort of the opposite relationship to what we knew was true. And at the time, we interpreted this as a simulation artifact rather than an actual modeled physical effect, and began re-evaluating the constraints of our simulation. And during this troubleshooting, we actually discovered that removing the aramid yarn and the layered acrylate resulted in a model that behaved exactly the same. And eliminating that excess geometry, as well as applying a coarser mesh, resulted in a model that converged in under 10 minutes, which made it much more practical for quick iteration and also allowed us to actually figure out what was going on. The final fix was actually to remove the rigid connectors that we were using to tie the ends of the fibers directly to the ends of the jacket. And these connectors were helping the model to converge, helping the simulation to converge for sure, but they also prevented the fibers from sliding relative to one another or rotating relative to one another. And we think that those extra constraints were introducing some artificial or preemptive jamming and resulting in those counterintuitive results that we were seeing early on. But SolidWorks simulations are prone to instability if they're left under constrained. So to replace those connectors, we added end caps to the jacket. And we left a tiny 0.01 millimeter gap between each end cap and the end of the fiber. And those end caps with that tiny gap basically allowed the fibers to remain completely free inside of the jacket as it shrank, but still allowed early enough contact to ensure that the simulation converged without equilibrium errors. You can also see the coarser mesh that we used there in the top right figure. So after setting up a working model, we set out to run an experiment to compare our simulated results with manufactured measured results. We again wanted to use a larger data pool, so we started by running 5 samples, and we varied the tension applied to the fibers between each of these samples to produce each with a different EFL. We selected multimode fibers for this experiment due to their sensitivity to bending, which makes them particularly suited for measuring the impact of EFL on attenuation. And the figure on the left shows the EFL we measured on each sample, as well as the corresponding tension we used to produce that EFL. And the data shows that 80 grams, for us anyway, corresponds to our near zero EFL approximation, as well as our hypothesized optimal running condition. After measuring the EFL, we measured attenuation on each of these samples, starting with a baseline room temperature, followed by measurements at -20, -40, and +70 degrees Celsius. Although the results for this experiment are all focused on temperatures of -40 degrees Celsius, because that's where the effects of shrinkage are the most pronounced. On the simulation side then, this is what our final setup looked like. And this is specifically for our highest EFL case. The simulated cable was modeled with a 2 millimeter OD subunit with 12 fibers and a length of 32 millimeters. And that length is just significant because with our EFL equation, it allowed for 2 full sinusoidal periods. And in previous work, we were using 5 periods, but again, this extra geometry was just adding to solver time and not really providing any additional information. And they're hidden here, but end caps kept the fibers from protruding outside the jacket during shrinkage, simulating a section of cable in the middle of a reel where the fibers are constrained. We applied the same fiber-to-fiber contact interactions that I mentioned earlier, which allow each of the fibers to press up against one another, as well as the inside of the jacket, which you can really see in that left-hand figure, those red hotspots showing where the fibers are touching, and right at the peaks, kind of where they are pressing up against the inside of the jacket. One jacket end face was fixed to constrain the model, and the other was left free to shrink. And we applied a uniform temperature load of -40 degrees Celsius to all of the surfaces. And you can see in that top right figure how the fibers are forced into the jacket and really fill up that inner diameter as they're compressed. So once we had all of this set up, we ran 5 different simulations to match our manufactured samples, and we varied only the amplitude used to represent EFL between each simulation. To collect the results, we probed the outside surface of each fiber in the contact pressure plot, and we exported that data into Excel to analyze. We applied mesh controls to the outside surface of each fiber as well as the inside surface of the jacket, And that allowed our number of nodes and elements in the simulation to remain fixed and basically just made our results directly comparable even across changing geometry. The end caps that we added did generate some artificially high stress, which you can even see there in the left figure. It's adding a lot of stress right to the ends of those fibers, which could obscure conditions in the middle of the cable that we care more about. So just to clean everything up, we also excluded about 0.4 millimeters from each end of the fiber data. This then is what our results looked like. So from that cleaned data, we analyzed the maximum contact pressure across all 12 fibers. Again, since we theorized that the localized stress hotspots were what were driving increased attenuation. And as you can see, the simulated data aligns very close with our measured data. The scales here have been adjusted, but again, we're really just looking for, is the trend of our simulated data matching up with reality? And this correlation represents a pretty significant step forward in establishing the simulation as a reliable tool for modeling real-world behavior. But just to further confirm the effectiveness of the tool, we applied it to predict attenuation in a new modified 8-fiber construction. Based on our previous test, 80 grams was established as a near zero EFL approximation. So using that as a baseline, we began to explore how small we could actually run this 8-fiber construction. And we did that by reducing the inner diameter in our simulation until we reached the minimum diameter at which we could still place all of the fibers without them overlapping. And at that minimum diameter, there was a pretty significant spike in contact pressure. But because the model doesn't account for things like aramid yarn anymore, because we removed that, we found this minimum was a little bit smaller than what we could actually achieve in practice. So after adjusting for machine and tooling constraints, we identified a more realistic minimum to start our simulations at. We next predicted the wall thickness required to maintain the same compression as our original 2 millimeter design. And to guide that decision, we modeled a short section of jacket and compressed it between 2 steel plates, which also mimics the setup that we used to measure compression in our manufactured samples. We started by modeling our original design and determining the force required to compress the jacket by 20%. We then reduced the inner diameter to make our smaller variation, and we applied that same force to the top plate and adjusted the wall thickness until our modified design achieved that same 20% displacement. And so that just allowed us to ensure that our modified design would maintain the same compression results as our original design. We ran 5 additional 8-fiber samples centered around the simulated optimized value, and the results once again show that contact pressure correlates very strongly with measured attenuation. The simulation successfully informed our choice of inner diameter to minimize attenuation as well as reduce overall cable size. And with the machine's capabilities established, we can continue to use this refined model to guide further design changes without requiring a sample run for every single iteration. So in conclusion then, this study successfully built off of previous work, demonstrating that a SolidWorks-based simulation can effectively capture the impact of EFL on internal stress and resulting attenuation in loose tube fiber designs. Our validation against experimental data showed strong correlation, establishing the tool as a reliable predictor of how EFL influences performance under thermal cycling, while things like finer meshes, aramid yarn, and layered acrylate can add to simulation realism, they also significantly add to solver time. Our simplified model reduced runtime from hours to minutes, making it practical for iterative design while still retaining accuracy. And finally, applying the tool to a new 8-fiber construction further established its value in guiding design decisions such as wall thickness and jacket diameter. And overall, our developed method provides a framework for faster, more informed optimization of optical fiber cables. These are the sources that I use to inform the project. They're also available in the full publication. And with that, I will take any questions.
Excellent, Devin. Thank you again for that informative presentation and very useful tool. Again, I think a lot of folks are engaged in trying to use this themselves. So we'll jump into a number of questions here. So what is the length of the model?
The length of the model, so we were using 32 millimeters. So originally, in sort of our original studies, we were looking at, we had, again, we're using this EFL approximation, which is just sort of a sinusoidal equation. So we were originally using a length of pi just because it sort of fit nicely in the math. But as we learned more about the simulation and sort of, the more geometry that you add, the longer it's going to take to converge. So we reduced that to 32 millimeters, which was, again, just enough for those 2 full periods, which was sort of the minimum that we needed to discover what we wanted to.
Right. And what type of material properties of the fiber jacket or other components were used in the simulations?
So actually, and you can still see my slides, right?
Yeah.
So I can actually go back, and all of this is in the paper as well. But this is the comprehensive list of
Got it.
all of the material properties we used, as well as the sources there along the top that we gathered them from. Yeah, so it was a lot of, and that's the thing is, there's not always a one size fits all material property, right? For a specific kind of material, each manufacturer makes them slightly differently, and so some of it was sort of compiling these different results and finding a value that was, a reasonable approximation, um, matched sort of by different research studies, finding what different people were saying the material properties were, and then um, from that trying to inform our own choice of material properties.
Right. And you can get these, from your supplier of the materials, but if any are missing, are they all required in order to have an effective simulation?
So that, yeah, that was a huge thing is, there, you're not, it's complex, right? Because you can get and that was something we ran into. You can get for example, the elastic modulus is not an uncommon thing for it to be supplied, right, with a material. Um, but the elastic modulus also changes if you're putting it under a cold temperature load. The room temperature elastic modulus is not at all the same as the elastic modulus at minus 40 degrees Celsius. Um, and so having to sort of interpolate, to get to results that match reality as much as possible, trying to gather as much of that information as you can. You don't need every single one of these. Like, you can even see in the figure there, there's certain ones that are hyphenated, which were ones that we couldn't find, and also were just not critical, to allowing the simulation to run. But there are certain ones that you really need, right? Which elastic modulus is a huge one, um, and coefficient of linear thermal expansion is a huge one, again, which is why we sort of just measured that one experimentally.
Right. And you may not want to go into great detail here, but what was the cable jacket material that you used to establish the accuracy of this simulation? And do you have an identification of the jacket itself?
Yes, I believe it was flexible PVC. It was a
Right.
soft PVC.
Yeah,
Um,
it's typical.
was there, sorry, I mean, I'm happy to discuss the specifics more, if
Yeah.
anybody wants to reach out, but it's, pretty standard.
Yeah, and obviously you can have flame retardant, flexible PVCs, you can have any number of types of materials. Um, why the von Mises stress is considered to check the stresses and not other stress options like principal stress available in the software?
Sure. So, well, let me see if I can get back to it here. So again, mainly we were looking for our actual recorded results that we were using to sort of make these predictions. We're looking at contact pressure, um, again, contact pressure, which is specifically the stress generated from surfaces pressing up against one another. The von Mises stress was not so much a hard metric we were looking at as just like it was a good, even just looking at the top right figure, it's a good demonstration that the material properties we entered are working, right? That these three layered surfaces are all exhibiting um, distinct stress levels, which you would expect, but you kind of never know until you look at the results. And so that's pretty much the only reason that was included there. Mostly we're looking at contact pressure.
And was an implicit or explicit solver used in the simulation?
Um, I believe it was explicit, um, but I'd have to double check that. There were definitely some how should I say, tweaking of SolidWorks settings required to not only get this to solve, but to get 5 variations of it to solve with basic similar settings. And so I believe it was explicit, but feel free I'm happy to follow up with that if anybody has specific questions and share
And
my settings
everyone,
as well.
at the end of the question period, you'll find or you'll see Devin's email address if you want to reach out to him directly and carry on the conversation. Um, Curiously, how is EFL applied?
How is EFL applied?
Yes, how
In
do you apply it?
in what context? In manufactured samples or in the
Yeah, I would
simulated?
imagine it was either quality control or manufacture. How how do you best use these results
Oh,
in your
sure.
simulations? Yeah.
Yeah, so okay, yeah. So at least in the experiments just to kind of get different EFLs, and I know there is sort of there's more advanced equipment for controlling the actual EFL, which we had started to look into and just didn't get far enough with. So just for the sake of this study, we literally were just increasing and decreasing the tension that we were pulling the fibers in at to get different EFL. And again, we kind of, it's pretty well established that lower EFL is generally better, or rather zero EFL is sort of what you want. Um, so more so, we were using the original EFL study to first just confirm that that was the case, and then second it was a good test case to determine whether or not the model was actually representative of real world behavior. So from this, we basically realized, yes, zero EFL is our best attenuation case. 80 grams corresponds with zero EFL. We're going to use 80 grams sort of going forward as our tension to achieve that EFL. And then use the simulation sort of going forward now that we've established its reliability to guide sort of more useful design decisions like the diameter and wall thickness, etc. Does that answer the question?
Yeah, I think that is how you're using it in the model. That's good. What is the reason for the non-uniform behavior in the graph attenuation versus EFL? Yeah,
Sorry, with attenuation versus
yeah,
here?
yeah, I believe so. Yes.
What? I'm sorry, and what's the question?
The what's the reason for the non-uniform behavior?
I'm not quite sure if I understand
Yeah.
what, just why yeah, I'm not quite sure if I understand the question.
Okay.
Because this is let's see, the attenuation is the average attenuation that we measured, um, and the red dotted line is the simulated maximum contact pressure that we measured in our simulation. So it's they're going to be different, and obviously the scales here are adjusted. So you're never going to match 1-to-1 with reality. Um, with a simulation, it's just never going to happen. And that was a big lesson from this project too, was just how do you find sort of the bare minimum that you have to do in the simulation world to get something that is predictive, right? And so it's not perfect, but from this we know that we can change certain parameters and we know that that's going to correspond with a change in the same direction in our real manufactured samples. So yeah, if there's a question beyond that, again, just reach out to me. But
yeah, no, I think that probably addresses the question. Have you applied the simulation and the validations to single mode fiber?
we have not,
Okay.
not yet. It was, yeah, it's just trickier. Because the single mode fibers are just less sensitive to those bending and to micro bends and stuff like that. So um, we were, again, just using the multi-mode fibers because we figured we'd be able to see the results easier. So we could for sure investigate using single mode instead of multi-mode, but again, this project was more so first just establishing whether or not this is even going to work, and so that would for sure be like a future step.
Right. On one of your last slides, how do you explain the contact pressure increasing as the inside diameter was increased?
Let's see. Um,
The contact pressure
yeah.
increasing as the inside diameter was increased.
So there's sort of a, from a surface level, um, let me just, yeah, so it's decreasing. Um, honestly, I mean, that's a situation of, you come into this study and right, your prediction, right, is that as you sort of reduce the inner diameter, you would think sort of imagine that linearly your contact pressure is going to increase, right, as you're decreasing that diameter, because again, you're just leaving less and less space uh, for the fibers to move around in. Um, and honestly, that's kind of what we thought was going to be the case as well. Um, and this is just a situation of reality is more complex than um, you know than what you might think it is. And I don't have a good explanation for why it sort of dips and then increases again. But this is a case of we ran the samples and this is what we measured. And we simulated the samples and we got the same response. So yeah, so I honestly I don't have a good answer for why that's the case. But the
This,
simulation matched with reality. So
yeah, it's still interesting, and it is, that's the important part, is that the simulation does match reality regardless of how it occurs. But
mhm.
um, and got a similar question. Have you been able to quantify the relationship between contact pressure and the resulting attenuation? And is there a specific relationship between attenuation and contact pressure from the simulation? And if
Like a
there are,
mathematical relationship.
yeah, what's the limits, and do you see this being a replacement for testing? I mean, if they
Oh,
are in
sure.
fact close enough, then yeah,
No. So
yeah,
on the surface, um, nothing is ever going to beat just testing the cable. I mean, you have to, right?
right.
I mean, it would be fantastic if you could just simulate it and say, okay, well, this is going to pass. Um, that's really one of the core sort of limitations with simulation, and sort of the limitations with the tool that we were using, because that's another thing to note is there are a lot of good and complex simulation tools out there. We were using for this the basic SolidWorks simulation toolbox. So it's linear static studies. And so you can get with sort of the advanced simulation toolbox and nonlinear studies, there's sort of a limit as it approaches infinity, right, of how close you can get to representing reality. Um, but sort of just the limitation, at least that we've run into of simulation in general, is you're never going to perfectly recreate what's happening in reality. There might be slight differences in the material properties. Um, looking at the elastic modulus, even just changing the elastic modulus a little bit is going to it won't throw off the trend, but it would like move that plot completely up or down, right? Sort of in the stress response. So at least in terms of how this was set up, looking at the stress numbers just as numbers doesn't really mean a whole lot unless you are running sort of multiple simulations and comparing them. And so that's kind of how we were, and are I should say anticipating and are using this tool is, you run a simulation of exactly the current design as it is, and then you change the thing you want to change and you rerun the simulation and you compare the two, right? And you see if your change moved you in the direction that you wanted or away from it. And that's kind of how we're using it to guide design decisions.
Right. A few more questions. What is the cable OD and ID for the 12 fiber case and the 8 fiber case?
So with the 8 fiber case, I think I wrote it on here. Our original design is 1.44 millimeters. The OD, I don't think I can. Well,
Mhm.
no, I can say. I think I actually did put it in here. These are 2 millimeter. These are both 2 millimeter cables. And so this
Mhm.
and the inner diameter we reduced from 1.44 down to, well, what you can see here in the figures.
Very good. Did
1.1,
you?
yeah.
Oh, okay, good. Did you define the temperature history in the model? And if so, what is the temperature defined?
Temperature history.
Yeah, did you define the temperature history in the model?
So I mean, I have maybe an idea of what this is referring to. So we again, excuse me, this is a linear static study, which just means that it's sort of applying the temperature in a linear fashion. So you enter a room temperature value, um, that is, well, it doesn't have to be room temperature. You define a starting point and you define an end point, a temperature load. And it sort of linearly extrapolates between those two. There are a lot of other nonlinear tools that you could use to make that more complex. So for the sake of this, it was just looking at that sort of linear interpolation between 0 and or rather room temperature and minus 40 degrees Celsius. I know we've done a little bit of work since then on um, even within the material properties, like I mentioned earlier, things like the elastic modulus can change with temperature, and SolidWorks does allow you to define those changes as well. So you can say it's this at room temperature, and then at minus 40 degrees, it's this. Um, and so maybe that's what temperature history is referring to. But I would
Well,
need
it's
more
probably
clarification.
as applied to real world cycling, and trying to see.
Oh,
I would imagine.
okay.
I would
Yes,
imagine.
yes, yes, yes.
Yeah, yeah.
Yeah, so that's something that we're kind of, you know, we in our original study, we wanted to, or I should say, I wanted to use, it would have been ideal to, if we had that database, right, um, of sort of previous samples, so that we could just kind of pull that historical data. Um, the main problem with using that for the first study was that we don't typically record EFL. We know where it's supposed to sit, and we measure it if there are concerns with it, but it's not something that we really keep, um, a strong record of. This is the EFL on every sample, and obviously we do have all of the historical temperature data. So I think that could be a really interesting study for the future. Um, Doing a study that doesn't involve EFL, right? Something that's just sort of attenuation and diameter, and maybe taking a look at how design changes over time and what how the simulation lines up with historical data. But for the sake of just establishing the tool, we just wanted to start with basically a clean study and a clean database, something that we had complete control over.
And I just want to say I appreciate all of the great questions that the audience has provided. Again, shows the interest in this simulation. Just two more questions here. At the
Sure.
on slide 19, is the maximum contact pressure referred to a contact pressure at a point or to an average contact pressure over the fiber length?
So this was actually the maximum contact pressure across all 12. So we looked at a lot of data for this, right? So it was, there's kind of what you think is going to be predictive, and then there's what's actually predictive, and sort of trying to match that up with reality. So we pulled essentially all of the fiber contact pressure data from each node, which you can see sort of here. So we're pulling all of that data and bringing that into Excel. This was the maximum contact pressure was literally of all of that data, the point that is the maximum, right? And so we did a little bit of filtering there, looking at like P95, and which is basically just saying, well, maybe not the very maximum point, but like, 95% of points were below this point, as well as sort of cleaning off the ends, which had those exaggerated contact pressure right at the end. So this is just looking at that sort of single maximum value and comparing that with the attenuation that we measured on the real samples. And I think there's a lot more statistical analysis you could do with this that we just wasn't within the scope of this project. But yeah, what kind of was within the scope was just here's what looks predictive with our first study, and then let's verify if this is predictive by using it to predict a new construction.
Right. And finally, what was the biggest challenge in getting this simulation methodology to work reliably and repeatably?
Yeah, and that sort of harkens back to several things I talked about earlier, but with the simulation, it's never going to one-to-one match reality. So figuring out what things were necessary and what things could go while still producing a model that was predictive. So learning how to remove things like, like the aramid and the layered acrylate to reduce solver time. Properly defining the constraints was a huge thing as well. And something that I think maybe even could still use a little bit of work. Even with the end caps, I think there are some more constraints that could be added to make the model more reliable. Because something that we ran into was when you have loose bodies in SolidWorks, they're become extremely sensitive to things like even just like the geometry and the mesh resolution. And so especially when you're using lower resolution meshes, you might have a sharp corner somewhere that pokes into another body in just kind of the wrong way and causes the model to just not converge or solve with, equilibrium errors. And so again, finding all of the settings where we could run 5 different simulations, with slightly different geometry and have them all converge with exactly the same settings was for sure a challenge.
Well, keep up the good work. Again, very applicable. And again, we're all trying to simulate things so we can have faster and more effective designs of materials and cables. So we really appreciate you spending the time delivering this to us again. Again, noting all of the questions. Clearly, it was an important topic. So thank you, Devin, for the great work.
Absolutely.
And we look forward to your continued contributions at IWCS in 2026 as well. So keep up the good work.
Will do.
Please note, Devin's contact points shown here if you want to reach out to him after today's event. And again, each one of these webinar series events are recorded and are archived on our IWCS.org website. It normally takes a few days or a week to get this up and running each time, but all of the webinars dating back almost 10 years now are all available on a variety of topics that will be useful to you if you want to go back and revisit. The IWCS webinar series is conducted several times a month. Our next scheduled webinar event will be a technical paper webinar on Friday, June 19th at 10:30 a.m. Typically, these are on the third Friday of every month at 10:30 a.m. Eastern USA time. Each of you will receive a notification, an announcement for these events, so please feel free to share these announcements with your colleagues so that they can also join in and register as well. Before we conclude today, I do want to recognize and thank our IWCS partner sponsors who contribute greatly each year to the success of our Cable and Connectivity Industry Forum. Without their strong leadership, their technical contributions, but also their generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank these leading suppliers in our industry for their support. So again, as I mentioned, this last week was exciting for IWCS. We put together a really compelling program for the 75th anniversary industry forum taking place the first week in November in Orlando, Florida at the wonderful Gaylord Palms Resort. We had over 100 abstracts for excellent technical papers that we reviewed last week and put together a great program. We hope that you'll plan to participate all the way through from the Sunday to the Wednesday. There are some really significant papers and events taking place through Wednesday afternoon, but also we have a fantastic celebration for the 75th on the Monday evening for a Cirque Royale, which unique to Orlando, Florida. So we hope you'll plan to join us and learn more about these incredible innovations. So stay tuned to your inbox, social media, as well as our website as information becomes available. The preliminary program will be available within the next several weeks. So stay tuned. Again, we thank you for participating today. Have a great weekend and look forward to having you with us again next month. Thank you. Take care.